Hello guys, in this video we'll be deriving kinematics equations, also known as equations of motion, using calculus, especially integration. Before we begin with deriving formulas, we have to know of something called the power rule. The power rule simply says that if you integrate a function of x, you simply take that function, in its exponent you add 1, then take your new exponent and divide with it. Then you add the c, which is the constant of integration. For example, if you will integrate a cubic function x cubed in respect of x, you will simply say that x cubed, on its exponent you will add 1, which is 3 plus 1, which makes 4. So you will divide with that 4. Then you add your c, which is the constant of integration, which at the end will give you 1 all over 4 x to the power 4 plus c. So this is how we simply derive using the power rule. In our previous grades, we know that the first equation of motion, it says that Vf is equal to Vi plus acceleration multiplied by time. So we can simply let Vf to be equal to just V and V initial to be V0. And we know that the second equation of motion says that Vf square is equal to Vi square plus 2a multiplied by delta x, which you can simply write it as V squared equal to V0 squared plus 2a change in x. And the third equation of motion that says delta x is equal to V initial multiplied by the time plus a half of acceleration multiplied by a squared time. We can also simply write it as delta x equal to V0 multiplied by time plus a half of acceleration multiplied by the squared time. So, perspicacious, how do we derive the first kinematic equation? We simply use acceleration, and we know that acceleration is given by dv all over dt, which gives us a dt equal to dv if you just cross multiply. Then from here you introduce the integral sign in both sides of the equation. So you will have integral a dt. So here you have to integrate in respect of time, which means you will say from t final up to t initial. And we know that the initial time, it is simply 0. So we will simply say from t up to 0, which is equal to the integral sign of dv. So here we are integrating in respect of velocity. So we will say from final velocity up to initial velocity. And we know that we said the initial velocity is just v0 and the final velocity is just v. So we cannot integrate in respect to t when there's no t here, which means t is right here next to a. It is just to the power 0. So let me put this inside the brackets. So the same thing to the other side. We cannot integrate in respect to v when we don't have v, which means v, it is also there. It is just to the power 0. So this is how we are going to write it. Let me also put it inside the brackets. So from here, acceleration is just a constant. We will take it out from the integral sign and we will put back our integrand. Then now you have to integrate. A is just a constant. If you integrate t to the power 0, it will be t power 0. On the exponent you add 1, which means your new exponent will be 1. Then you divide with 1. It will be just a multiplied by t. So you just put back your evaluation bar from t up to 0, which will be equal to, even on the other side, v, the exponent is 0, you add 1, then you take your exponent, you divide with it. V divided by 1 is just v. You put back your evaluation bar, you say from v up to v0. So from here, if we substitute t, it will be a multiplied by t minus, if we substitute 0, it will be a into 0, which is equal to, if we substitute v on the other side, it will be v minus v naught. Then on this side, it will just give us at, because a into 0, it is just 0, which will be equal to v minus v naught. So if we arrange this one, v will be equal to v naught plus at, which is actually our first equation of motion. So this is how you derive it. So let's jump to the third equation of motion. What you have to do, you take this first equation of motion. You know that v is given by dx all over dt. So you will expand it and equate it to v naught plus at. Then after this, you have to cross multiply, which will give you dx equal to into v naught plus at. Then you multiply all of it by dt. Then the next thing that you have to do, you introduce the integral signs from both sides of the equation. So it will be integral from x final up to x initial of dx, which will be equal to integral from t up to 0, which is the final time up to the initial time. So again, you know that you cannot integrate x if x is not there. So x is there, is just to the power 0. So integration of x to the power 0 in respect to x is equal to v naught multiplied by t to the power 0 plus acceleration multiplied by time. So from here, you integrate your x to the power 0, which will be just x, and then you put back your evaluation bar from x final up to x initial, which will be equal to v naught multiplied by t plus at squared. Since your exponent is 2, you also divide with your 2 from the power rule. Then you put back your evaluation bar from t up to 0. Then you have to substitute with x final, then minus x initial if you substitute, which will give you, on the other side, you first have to substitute with t throughout, then you minus when you substitute with 0. So it will be v naught multiplied by t plus 1 all over 2 at squared. Then you have to minus when you substitute with 0. And obvious, v naught multiplied by 0 and at squared, if you substitute 0, it will all just give you 0. So it will be just minus 0. So x final minus x initial, it is just simply delta x. So here we will have v naught multiplied by t plus a half of acceleration multiplied by the squared time. So this simply makes our third equation of motion. So let's look at how we derive the second equation of motion. Again, we will use the equation for acceleration. We know that acceleration is given by dv all over dt. How about I say acceleration is equal to dv all over dx multiplied by dx all over dt. Still, I didn't violate any mathematics rule because dx will just cancel with dx. But again, I know that dx all over dt, it makes velocity, which means I can say acceleration is equal to velocity multiplied by dv all over dx. So from here, what you have to do is to just cross multiply. So you will get a dx equal to v dv. Then the next thing, you introduce the integral signs in both sides of the equation. So if you are integrating a dx, which means it is in respect of x, you will say from x final up to x initial, which will be equal to your integration of v in respect of v. So it will be from your v up to your v naught. We know that a is just a constant, so we will take it out. And you will be left with x to the power 0 because you cannot integrate x when you don't have x. Multiplied by your dx, which will be equal to your integration of v in respect to v. So integrating x to the power 0, it will just give you ax. You put back your evaluation bar you say from x final up to x initial, which will be equal to, when you integrate v, you will get v squared divided by 2. You put back your evaluation bar from v up to your v naught. Substituting here your x final, it will give you ax final minus ax initial, which will be equal to 1 all over 2 v squared minus 1 all over 2 v naught squared. From here we know that x final minus x initial is just change in x, which means on the side we will have a change in x equal to 1 all over 2 v squared minus 1 all over 2 v naught squared. So then what you have to do, since we have fractions, you just have to multiply throughout the equation by 2, which will then give you 2a change in x equal to 1 all over 2 v squared. If you multiply with 2, it will just give you v squared minus 1 all over 2 v naught. If you multiply with 2, it will just give you minus v naught squared. So if you rearrange this to make v squared the subject of the formula, it will give you v squared equal to v naught squared plus 2a change in x, which is your second kinematics equation. So this is how we simply derive the 3 kinematics equation. Don't forget to like and subscribe on Perspy Science to be updated with more videos. Thank you.